100% drawing, but if we only can use the hand to sketch it, I think that just like the group locus, we can always calculate at any point of the interest, we can calculate the very detailed numbers. So most of the time, the sketching method will be more useful because I can give an overhead, the kind of the head up of the systems. And here I'm going to have the introduce, before we really introduce how to sketch, and I'd like to define a few keywords. And for the Bode plots, so basically, so the Bode plot can be applied to any systems. The GS can be general, can be open loop system, can be closed loop systems. Okay, so it consists of two portions. The first portion is the magnitude. So this is the magnitude of the G, and in terms of the J omega. And the second portion is for the phase. So this is the phase of the GJ omega. Okay. So when we draw the Bode plot, basically we have the magnitude, the second one we draw on the phase. And usually this one is taken on the log scale of the frequencies. Okay, so for example, in terms of log scale, basically say this is 1 and this is 10. This is 10 to the square. They basically equal space in terms of the order of the magnitude. For example, like this. Okay, and usually we have the curve will be like this. Then we can have this certain say if this is the magnitude, the curve for the magnitude. And say corresponding to here, and if I would have the magnitude for phase, would be like this. So basically here you can see, pay attention to the intersections of the curve, magnitude curve or the phase curve to the horizontal axis. And that is where we have the few things going to define. So this one is the intersections of the magnitude curve to the log scale, and here we define this particular, it's called the omega G, and that's called the gain crossover. Frequency, that's the omega G. Okay, and here we define the omega. The P, I think in terms of, yes, P. And this one basically defined as the phase crossover. Frequency. We define it as a omega P. And most of the time, the system will be like this. And for certain systems, they could be omega P is less than omega G. Depends on the system type. It depends on the description of the system. But here, this is a stable system. That's what we're going to say. So here I show is a stable system. And in this case, corresponding to omega G, the gain crossover frequency here, we have corresponding to here, that is basically omega G is here, okay? And so for this case, we define the magnitude. In particular, that magnitude is measured from about 180 degrees. So this one defined as we call the margin of the phase and phase margin. This magnitude, for example, here you can see this number is say minus 20. Okay. So minus 20 is above the minus 80 by 60 degrees. So this is called the phase margin here. Okay. And on the other side, at omega p, at the phase crossover frequency here corresponding to, we have the gain margin here. So let me put it into here, okay? So for this case, this is omega p, and this is the gain margin here. For this particular example here, the gain margin is measured from the magnitude equal to 1. Okay, so this level here corresponding is g j omega equal to 1 here for this level. In particular, we define. Okay, so that means the gain margin. Gain margin is simply is this magnitude. Gain margin is the magnitude of the gain respect to 1. For example, if this number here is 0.1, okay, then the gain margin equal to 10. Okay, and that is the measurement. Basically, is something like this. Okay. So here we have defined the keywords here, and so how many here we defined? We have for the frequency, we have a gain crossover frequencies, we have a phase crossover frequencies. In terms of the magnitude, we have the magnitude in the phase diagram. We have 3 phase margin, and then in the magnitude we have gain margin, that's the number 4. And furthermore, for systems, if we have said this is a log omega, and this is the g j omega, and for the magnitude, we have a further system. For example, if the system is something like this, okay, this going down here. If the system behavior have the peak at a certain frequencies here, so that means here we define it's called omega r. That means the resonant frequencies. Okay. And this usually at the very small numbers omega, that magnitude is equal to 1. Okay. And if we scale this one equal to 1, then we can define the bandwidth. Bandwidth is defined by this. Compared to the initial magnitude, if we take the one of the square cube, and then we measured the magnitude, the span in the frequency is such that the magnitude of the response is greater than the one of square cube. So basically here we measure this is called the bandwidth. So basically bandwidth is the regions in the frequency, a portion of the region in the frequency, and that bandwidth give us the definition is we pretty much sure the magnitude of the output, the magnitude of the systems is at least this one is 70% of the original value here. Okay. So here we have, this is the 5th keyword, and this is the 6th keyword. So with those keywords being defined, then we can gradually learn how to sketch the Bode plots for individual systems. We have quite a few we can try to go over. So start with